Okay, so this is going to be a pretty quick run over for your the things we have covered since we have been in this semester together. So lessons 1 through 8, we're just going to go very quick. So we talked about the kinetic molecular theory and how they related to gases. We reviewed it. All of the things we learned, I guess, in the last semester or should have learned in the last semester. And I told you guys to review Chapter 9 if you weren't completely solid on the material. And then we turned our attention towards liquids and solids and how these aspects of the kinetic molecular theory apply differently or not at all to liquids and solids. And then we talked about Coulomb's law, which is going to basically arise as some attractive forces that exist between molecules of the same substance. Remember, we talked about intermolecular forces are between molecules of the same type, and intra are the interactions that occur between molecules of different types. So inner is within, and intra is on the outer. The intermolecular forces that we talked about were ion dipole, dipole-dipole, dispersion forces, and hydrogen bonding. When we defined intermolecular forces, we said specifically they're attractive, and mathematically we relate this by using Coulomb's law, which is between charged particles. And we want to treat them always to be an attractive force, therefore we have a positive and a negative. And remember, I said don't really worry about the formula and using it, but knowing that there's a variable of distance, that as the charges get closer, the energy or the force goes up, kind of like magnets. So according to Coulomb's law, the attraction between two particles is greatest when the charges are opposite and the particles are closer together. We reviewed a little bit about ionic and covalent compounds. Ionic compounds are where your electrons are transferred, covalent is where they're shared. This arises to a difference in the overall charge. Ionic compounds have what's called full charges because they have exchanged electrons, whereas covalent compounds will have partial charges. And we assign these using electronegativity. And then we said that these partial charges arise to some differences in our intermolecular forces. So you see here that powerful attractions cause ionic compounds to be solid at room temperature with high boiling points. So thinking of things like NaCl, you usually don't melt NaCl. Whereas the intermolecular forces that are present in covalent compounds are considered to be weaker, but they are still important. And so covalent compounds could be solid, liquid, or gas at room temperature, depending on the strength of the intermolecular forces present for that compound. And so then we reviewed a little bit about geometry, polarity, electronegativity. Again, this is chapter 7 and 8. If you're not solid on the material, it's a good time to go back and look. We talked about covalent versus intermolecular. So covalents are strong forces between atoms within a molecule, whereas intermolecular forces are weak, attractive forces between separate molecules. So instead of the bond in water, we're talking about the bond between two waters. Okay, and not to say a covalent bond between two, but a force between two. So then we looked at this diagram where we had gas, liquid, and solid, and we talked about how we are breaking only intermolecular forces as we go from pitcher to pitcher. We are not breaking any of the covalent bonds at all because this is consistent with the phase change and not a phase change which is a physical change and not a chemical change by breaking the bonds. So then we talked specifically about the forces. The ion dipole was the first, and this was a force that exists between a cation, like sodium or magnesium, and a polar molecule, or an anion like chloride or bromide and a polar molecule, with the most common polar molecule probably being water. And so we reviewed dipole, knowing when a dipole is present. We looked at this relationship between sodium and chloride and the water molecules, and why the water points in one direction and points the opposite in another direction with the chloride and then the magnesium. We talked about how this is called hydration. The waters surrounding the cation and the anion is a a process called hydration. Then we talked about dipole-dipole and dispersion, and dipole-dipole is an attractive force between one between one polar molecule and another polar molecule. So these are things that typically have halogens, oxygens, nitrogens, with something that's further away from it on the periodic table, because we're talking about a disparity in the electronegativity values. Then we talked about dispersion forces, which is the weakest, and because the electrons are moving, it induces what's called a temporary dipole, which allows us to have a dispersion force which is attractive enough so that it holds molecules together into a liquid and a solid state. So then we ranked our intermolecular forces. We had ionic and covalent bonding, then there was hydrogen bonding, ion dipole, dipole-dipole, and dispersion. Okay, with the last three on here being what we called, not the last three, hold on, let me highlight them, with the van der Waals forces. I think we get that down here at the bottom. Okay, so I don't want to jump ahead. Okay, so the van der Waals is a combination of the three. Okay, so I'm kind of jumping ahead. Of the three, those are our van der Waals forces. Okay, so then we spent some time kind of looking at the strongest intermolecular force. Remember that if hydrogen bonding is present, dipole-dipole and dispersion is present. If dipole is present, dispersion is absolutely present, but hydrogen bonding may not be present. And in some situations, dispersion force is the only force present. Okay. So we looked at some examples, geometry, dipole, moment along the bond, and then we talked about hydrogen bonding. The importance here is hydrogen bonding, you must have a NOF present, and we looked at some examples of hydrogen bonding, and then looked at some examples of what could and could not hydrogen bond to itself. Okay. Then we compared van der Waals forces, which we talked about a little bit up there. And then one of the last things we did was talk about how boiling point changes in relationship to two factors. One is intermolecular force, and the second is molecular weight. And so the greater the molecular force present, meaning hydrogen bonding, dipole-dipole, and dispersion. Okay. So if hydrogen bonding is present, it's going to have a higher boiling point than if something only has dispersion forces. Then we looked at molecular weight. The higher the molecular weight, the greater the surface area, therefore the more intermolecular forces, therefore the higher the boiling point. Then we talked about lesson 2 is phase changes. We talked about the phase changes between solid, liquid, gas, and energy and heat being added in. And we defined the enthalpies of the fusion, sublimation, and evaporation. We talked about the fact that the strength of the intermolecular forces, the temperature, the atmospheric pressure, and kinetic energy of the system affect whether a molecule will leave the liquid state and join the gas state. And that the same idea rules these other 4 phase changes. We talked a little bit about the enthalpy signs, phase changes in thermodynamics, but we did, if we go down, we did eliminate this math for right now because we are going to get into a chapter at some later point in the semester where we'll talk very extensively about thermo. This diagram, if you'll remember, we talked about how as we're adding temperature in, at some point the temperature is, the heat that's being added in is only increasing the temperature. And then depending on what the material is, in this case, we'll say it's water, at 0 degrees Celsius, then we are going to have the melting occur. And so all heat being added in is only going into making a phase change occur. Once all of the solid has become liquid, now the heat being added in goes back to increasing the temperature. Excuse me. At 100 degrees Celsius, boiling will begin. So we start the transition between liquid and gas, and all the heat going in is only going into the phase change. And then at some point, once all the gas is formed, then the temperature, the heat going into the system would only result in an increase in temperature. So this was an important thing we talked about. Then we talked about phase diagrams. We spent a lot of time on phase diagrams, so you need to review this. It's very important. We're going to see it. It's on the ACS final. We talked about the different areas, solid, liquid, gas. We talked about where the phase changes exist along the lines. We have the solid to gas, we have the solid to liquid, and the liquid to vapor or gas. We talked about finding the melting point and the boiling point. We talked about the triple point. We talked about the importance of the backslash and the forward slash and how it tells us something about the densities of the liquid and the solid state. Okay, so make sure you know phase diagrams very well. Okay, most likely we are not going to see a supercritical fluid on the test just because it's not typical. Most phase diagrams that we're going to see are going to be simple phase diagrams, or if they are complex, it's only because there's going to be additional solid states like the carbon one that we see right here. Okay, so that's all of lesson 2. In lesson 3, we started talking about types of crystals. So we talked about ionic crystals, ionic compounds, and how the formula unit that we see here, the arrangement of the cations and the anions. We talked about the properties of ionic crystals, so make sure you remember those. Then we talked about covalent compounds and how their particular arrangement, this is carbon, this is graphite and diamonds. And then we defined some characteristics of molecular crystals. So I told y'all to make sure that y'all read these, but in the book, and I wish I had my book with me, in the book there is a section which will talk about the properties of ionic crystals and covalent crystals and molecular crystals, and I have to think of the last one, metallic. Okay, so make sure there's a table where it has like melting points, and it talks about conducting electricity, and it'll tell you if it's high or low or non-existent. Okay, so make sure you know that table because that's all of this material right here. Okay, so we talked about molecular and metallic. I told you to go read those things. And then we talked about something that is amorphous. Okay, so when something is amorphous, it lacks a regular 3D arrangement of atoms. And so if we see here, we have a very regular shape, and then some of these shapes here are very irregular. Okay, so this would be amorphous, and this would be crystalline. Okay, and it's glass, and that's irrelevant. It's just a matter of seeing the irregularity on the right and the regularity on the left. So then we talked about crystal structures. We spent some time on this, and our quiz, the first quiz was on this kind of stuff. So we kind of backtracked a little bit and talked about properties of liquids. So we talked about, this was part of your quiz, and how this arises to surface tension, which is cohesive. We gave a few examples. We said why. Then we talked about cohesion and adhesion. Viscosity, this was the quiz question that the reason why you warm your car up is because as the temperature increases in your car, the oil in your car also the temperature increases, and therefore the viscosity of the oil goes down and it runs smoother. Okay, or I guess I shouldn't say just the oil, but the gas, the oil, all of the components in your car will run better when there's a lower viscosity. Okay, so we're looking for the word viscosity. Then we talked about why water has a lower viscosity than many other liquids and why that's important. The terrible Boston molasses flood. We talked about the unique structure of hydrogen bonding when it's in the solid state and how it can make 4 total NOF bonds, which provides extra stability. The extra stability requires extra energy than to overcome, which is why water has a boiling point of about 100, which is fairly high for a liquid. We talked about why ice floats on water, that it's not about the mass, it's about the volume, the area in which it takes up. And then we talked about crystal structures, and we again redefined crystalline and amorphous. We talked about unit cells and lattice points and the crystalline solid. And then we said don't necessarily worry about memorizing these, but just realize that there are different shapes. They don't all have to be parallelograms, and they don't all have to be just cubes. Okay. Now in this class, we do get to treat, or we only focus on the cubic structures, which is the first one. And we had 3 different kinds, and I told you that your quiz would be on this, and it was. And we had simple cubic, which is a unit cell where you only have 8 lattice points at each corner. And because those lattice points are shared 1/8, actually only one atom exists in the box, one unique atom. So each box here would have an atom, one unique atom inside. Then we talked about body-centered cubic, or BCC, and how this is body-centered because it has the 8 lattice points at each corner, and then it has one entire cell that's wholly inside the bottom of the box, in the body of the box, which gives us 8 lattice points shared 1/8 of the time, one lattice point which is shared 100% of the time, which gives us 2 atoms. And this is where the quiz was RBI. One atom was the rubidium that was wholly in the box, and the iodine was the atoms that were split 8 ways on the corner. Then we had face-centered cubic, FCC, and on face-centered cubic we have the 8 lattice points on the corners, and then we have 6 lattice points, one on each face of the box. Because the faces are shared between 2 boxes, the 6 lattice points were shared 50% of the time, and that gave us 3 atoms, and then the 8 corners still gave us 1, which means in the face-centered box we have 4 atoms. Then we talked about the edges, and even though that didn't show up specifically, it is an arrangement that's possible. I did tell y'all to make sure you read about the hexagonal close packed and the cubic close packed cells right here, and that there was a question on your homework regarding it, but that this is test material that comes from the reading. Okay, so you'll see something on your test which will be solely based on the fact of did you read the material that I told you to. Then we did a practice problem, and then there was a set of guidelines there at the bottom just to reiterate those rules, and a very simple list at the end. Okay, so this ended chapter 11. Chapter 10. Well, I don't even know. Let me see. That is chapter 10. Then we went to chapter 5, which was solutions. So there was a lot of review in this chapter that we moved into, which is nice, but then we ended with a lot of new stuff. So we talked about components of a mixture, what is a solution, solute, solvent. We talked about 3 different types of solutions based on how much solute is dissolved. We had unsaturated, saturated, supersaturated. We talked about making supersaturated solutions, how they're not very stable. This is why the soda can in the problem, when you open it up and the CO2 escapes, that's why it's supersaturated, because it's not stable. Eventually, it's going to separate. Okay. Inner workings of solutions, we talked about the 3 intermolecular forces which are present into making a solution, how we have to break 2 of them, which is the solutes and the solvents, in order to make solute-solvent bonds. Okay, and this is heat energy. This is a lot like Hess's law. So when we have an overall enthalpy value that's negative, the solution process would produce heat, and when the overall enthalpy value is positive, it would be a cooled solution upon mixing, so it would feel cool, which is endothermic. We talked about how enthalpy and entropy, which we will see entropy a lot when we get to that thermo chapter that I told you about. How enthalpy we think of heat, entropy we think of disorder. So if we look at here, this is entropy, very nicely ordered. This is very disordered. So we can see that this process of making a solution increases the entropy. Then we talked about the fact that there's a general rule which predicts whether two substances will mix based on polarity. Like dissolves like. This was your quiz question. I told y'all it would show up. I went or and that was like dissolves like. You need to know that rule. It's a very important rule. So what that meant was nonpolar substances dissolved nonpolar substances, and polar substances dissolved in polar substances. And this could be dissolve or mix. And then nonpolar and polar, they do not dissolve each other. They do not mix. We looked at benzene and carbon tetrachloride and tried to see, did they mix? And we said yes, they did, because they're both nonpolar. We call them miscible if they're liquids, immiscible if they're two liquids that don't mix. And then we talked about the fact that when a molecule or ion is surrounded by solvent in a specific manner is known as solvation. Earlier we saw this called hydration. Okay. So we moved to lesson 6. You had your quiz. Your second one had material from lesson 6 on it. I posted these answers on Canvas, but you need to know percent by mass. It's an important formula. Mole fraction, molarity, molality. If you don't know these formulas, these problems are going to be impossible to do, so make sure you know them. And then, just to review, we talked about those, but we don't see them very often in each chapter, those units of concentration. We did a converting between units, so your quiz was this. Okay, and then we did molarity and mole fraction as well. Okay, so make sure you review making those conversions. Then we talked about solubility. We talked about the effect of temperature and pressure, and then we looked specifically about solids in water, and that as we increase the temperature, the solubility of a solid tends to also increase. We looked at solubility curves, so you can see all the lines going up show us that as the temperature increases, the solubility increases. There's just a few examples maybe where that's not true, right here and right here. However, for the most part, we can see that they are a positive relationship. We said we were not worrying about fractional crystallization. It's a specific technique that's useful, but it's not within the scope of the course in the book anymore. The gases in water had the opposite relationship with temperature. As we increase the temperature, the solubility of the gas decreases, meaning the gases are going to escape from solution as we increase the temperature. We talked about global warming, which should hopefully help you to remember that relationship. We also talked about solubility curve in action. You might have thought of other examples, but sodas to me or carbonated beverages are the ones I think of first. Then we talked about the effect of pressure. Solids in water, pressure has no effect on the solubility. However, when it's a gas in water, the solubility of gases is described by Henry's law. So we looked at that, and it is C equals Kp. And we had concentration, pressure, solubility constant. We talked about how the units are expressed in molarity, so that's important because that's the whole term. It just says C, it doesn't say molarity. So make sure you know that formula. There was a sapling question on that as well. We talked about not addressing the kinetic molecular theory and how it relates to Henry's law, but simply using Henry's law to explain the effect of pressure on the solubility of gases in water. We talked about why sodas gradually go flat when the bottle is left open. That's because the CO2 will escape and the soda will eventually go flat. Then we did a problem over Henry's law. Okay, so review that. And then we talked about two important exceptions to Henry's law. One is that when a gas reacts in water, it will become more soluble than what we originally predicted. And then when we have oxygen in blood, we know that hemoglobin is there to assist the solubility of oxygen by binding it and keeping it in solution, which we need. All right, then the final lesson was colligative properties. This was a big one because there was a lot of new stuff. These are the 4 colligative properties. I recommend you memorizing vapor pressure lowering, boiling point elevation, freezing point depression, as 3 words each time. Don't just try to remember vapor, that, and freezing. These words at the end are just as important as the colligative property itself. Then we looked at things as electrolytes and non-electrolytes separately. So these are ionics versus covalents. We started with non-electrolytes. We did vapor pressure lowering. We talked about this formula right here, which is so important. And we did an example. Remember, vapor pressure lowering formula is the mole fraction of the solvent. So down here, when we were solving for the mole fraction, we had water and we had glycerin, and we needed the mole fraction of water, which was our solvent, and got the new lower vapor pressure. We are not going to use Raoult's law using a volatile solvent, so a volatile solute. We are not going to worry about that. And we are not going to worry about fractional distillation. You will see that in OChem, but we're not going to worry about that now because we are omitting this formula. Okay. Then we talked about boiling point elevation, which should indicate an increase in the boiling point. And we looked at the phase change diagram and how the lines would change. And there was even a sapling question on how these lines would change. And you should, if you haven't done that yet, you need to go look at that particular question. So then we talked about why solute increases the boiling point. And then we looked at the boiling point elevation formula, which is delta TB time is equal to a constant times molality. We did a problem with benzene and a C10H12O2 solute. And just remember down at the end, what you solve for in the delta TB formula is just a change. The final step is then to add it to the normal boiling point. Freezing point is the same, except we need to subtract it and not add it. And I said this is a big mistake that students make, so make sure you don't make that mistake. Then we talked about osmotic pressure, which is the pressure required to stop osmosis, which we defined up here. This is the formula with molarity, gas constant, make sure it's this one, temperature in Kelvin, and osmotic pressure in ATM. We did a problem. Remember this one, we assumed STP because we weren't told, but I told you I would tell you, and I will. I uploaded the YouTube video earlier for the molar mass determination, so go watch that if you haven't. Then we talked about electrolyte solutions, and that the only difference is that they dissociate in solution into separate particles, they're separate ions, whereas non-electrolytes do not. They stay as a molecule. They do not dissolve into separate components. And so what we're going to have to account for is the amount of ions produced when the compound's dissolved, which is the Van't Hoff factor. And so we inserted an I into all of our formula, which is the number of actual particles in the solution after dissociation. So if they don't dissociate, like sucrose, I is equal to 1. If they do dissociate, we predicted these numbers right here. So really, things that dissociate, they magnify the effect of the solute's presence. Okay, meaning the vapor pressure is super lowered. The freezing point is super lowered. The boiling point is super increased. Okay, the osmotic pressure is super increased. Right? So that's the only difference. And so we did an example using I, and then the one thing here, you'll see I deleted one of the questions about predicting the Van't Hoff factor, but there's this, it's not always true that they 100% dissociate into sodium and chloride. Okay? The idea is that of all the sodium chloride, maybe only 95% of them will dissociate. So there's actual, there's calculated values, what we count, and then these are the actual measured values. And you can see they're not, some of them are pretty far, like magnesium sulfate it's 1.3 when we actually think it's going to be 2 whole molecules. But for right now, conceptually, I just need you to know that they don't 100% dissociate. We're going to talk about dissociation a little bit later, but for now, when we're doing the formula calculations, we're going to assume that they 100% dissociate. Then I told you to make sure you read about colloids and, let's see, where's the other? Colloids and, won't stop, there we go. And emulsions. Okay, there's a whole section with this that's got definitions and things like that that you need to go and read. It's kind of like they're in between. They're not heterogeneous. They're not like trail mix where you can very easily pull out particles, but they're not exactly homogeneous. So things like milk, things like a muddy creek. If you stand in the creek and the silt rises up and it looks really muddy and cloudy, but then over time it could settle out. So, and those are things like suspensions. And so you need to go read about these mixtures that are not purely homogeneous, but don't quite qualify as heterogeneous. So another reading thing to make sure you do. So this should hopefully help you. Just a very quick Cliff Notes version of what we've learned in these first 8 lessons. I'll post this on YouTube. You can watch it. Hopefully this is not the only thing you're doing to study, but if it is, I guess it is better than nothing. Good luck, and I will see you on Monday.